All right, everyone. Welcome once again to the set theory seminar. Today we have Philipp Lücke, who is currently at the University of Barcelona. And he's going to speak about large cardinals, strong logics, and reflection principles. Philipp, go right ahead.
Hey, thank you very much. It's a great pleasure to speak in the seminar. It's also very nice because there are a lot of connections to people in the New York area in this talk. So first of all, so 2 years ago, I gave a talk in this seminar, and Vika and Gunther, they suggested that I should prove some result, and I actually did it afterwards. And this is kind of a lot of the stuff I will talk about builds up on this. And also some very nice discussions I had with Vika and Will Boney. They also motivated quite a lot of this work. Okay, so I will talk about large cardinals, strong logics, and reflection principles. And you should feel free to interrupt me and ask me to go back, because there will be quite a lot of definitions in there, because one of the themes is that I will talk about certain patterns repeating in the large cardinal hierarchy. So you will see a lot of variations of definitions. So please feel free to ask me to go back to some definition. Okay. Okay, so I would start with a very general introduction. Okay, so starting with Cohn and Gödel, we know that there are natural mathematical questions that are not answered by ZFC. So there's this program to search for new axioms for mathematics, or extensions of ZFC that answer these important questions. And in this search, large cardinals play an outstanding role, and for several reasons. Okay, so first of all, so the large cardinal axioms tell you that there are certain large cardinal numbers that they are so large that you cannot prove their existence in ZFC because they imply that consistency of ZFC itself. And one reason why they are important is that they answer many natural questions in the desirable way, and therefore they are strong candidates for new axioms. But also, large cardinals can help us to analyze other axioms. So we can use them to measure the consistency strength of other candidates for new axioms and order them into a linear hierarchy based on consistency strength. But despite the central role, there are still many open fundamental questions surrounding large cardinals. And let me give you 2 examples of the maybe main ones. So first of all, what is a large cardinal? So we have kind of an intuitive understanding of what large cardinal axioms are, but some of them, they can look quite different. So we can talk about embeddings, we can talk about partition properties, we can talk about something like Popenka's principle or zero sharp, and they kind of look very different. And there's no definition of what a large cardinal is. And without such a definition, it seems kind of hard to prove very general statements about large cardinals. The other main question is, are these axioms true? So they answer many canonical questions in the desirable way. For example, they give us a canonical theory of definable sets of reals. But this kind of, it's not a direct reason to accept them, because we could also just accept the consequences as new axioms, right? And therefore, it's kind of open whether we should add large cardinals to our rules of mathematics. And I think a very fruitful way to approach these very general, broad questions is to consider equivalences between the following 3 types of statements. So first of all, large cardinals, and then compactness properties of strong logics, or logics extending first order logics. And finally, reflection principles that extend the statement of the Löwenheim-Scullin downwards theorem. And here it's important that now we're talking about equivalences, right? So we are not talking about implications. So I think this type of result gives you a much stronger reason to argue to accept large cardinals, because when we have the question, should strong logics behave nicely? And when I guess the answer, there are good reasons to say yes. And if we say yes, then we actually accept large cardinals to exist. Okay. So let me give you maybe the main example of such equivalence, and they deal with Vopanka's principle. So Vopanka's principle, there are very many ways to formulate it, but maybe the standard one is to say for every proper class of structures of the same signature, we can find an elementary embedding from one of the structures into another one. So we can restrict this to graphs and it's still equivalent. So this is a scheme of axioms, and this was actually recently used to answer a lot of long-standing open questions also outside of set theory. So for example, in category theory, in algebra and homotopy theory. And set theorists view this as a large cardinal axiom. I will tell you soon why. Okay. So Joan Bagaria, he gave a nice presentation of this principle in terms of elementary embeddings. And for this, we need two notions. So first of all, we define Cn for a natural number n to be the class of all ordinals, such that the corresponding initial segment of the universe is sigma n elementary in the whole universe. So these are the sigma n correct ordinals. And once we have this, we can define Cn extendable cardinals. So at the moment, you don't have to remember this definition. So it's just it will appear in the next theorem. But it's an extension of extendability. So now we say that some cardinal kappa is Cn extendable if for every larger ordinal we can find an elementary embedding from the given initial segment of the universe into a larger initial segment of the universe, such that the critical point is the cardinal kappa. It gets mapped above the ordinal lambda, and the image of the critical point is in Cn. Okay, so extendable cardinals are just C1 extendable cardinals. So this strengthens this. And what Joan showed is the following. So over ZFZ, the following schemes are equivalent. So Vopanka's principle and the assumption that for every natural number, there's such an Cn extendable cardinal. And that's the same as saying for every n, there's a proper class of these cardinals. So this gives us a nice large cardinal characterization of Vopanka's principle. And now in the other direction, so let's talk about strong logic. So Vopanka's principle is also closely related to compactness properties of strong logics. And for this, I need to tell you what an abstract logic is, and I will not give the full definition, but it's basically the following. So an abstract logic is a pair consisting of a class function L and some satisfaction predicate, such that this class function, it maps signatures. So just as in first order logic, we have signatures are sets of constant symbols, function symbols, relation symbols with given arities. And this function maps this set, the signature to a set that should be seen as a set of sentences in the logic that I can build from this signature. Okay. And the other thing is that I have a satisfaction relation. So I define models again as in first order logic. So they have a domain and they interpret constants, functions, and relation. And this relation tells me when a given sentence is true in a structure. Okay, and then I want these two things to satisfy certain canonical rules about invariance under isomorphic copy and extensions and restrictions of signature. And I want some boundedness of the sizes of signatures that generate sentences. So in first order logic, every sentence is generated by a finite subset of a signature. And for an abstract logic, I just want some cardinal kappa such that whenever I have a sentence that's in the image of such a signature, then I want a small subsignature, so size less than kappa, that also generates a sentence. Okay, so this is just a very broad way to define what a logic is. And all of the strong logics that one wants to consider, they fall into this framework. I mean, maybe except for something like L odd odd, where you can build for every ordinal, you can build the corresponding disjunction and conjunction, for example. So there's no boundedness there. But everything where something like everything is generated in a bounded way, it falls into this framework. Okay, so this is an abstract logic. And now I can say, I now want to generalize the compactness theorem for this logic. So given such a logic in the cardinal kappa, I'd say that the theory is less than kappa satisfiable if every subtheory of size less than kappa is satisfiable. And some cardinal kappa is a strong compactness cardinal for the given logic if every less than kappa satisfiable theory is actually satisfiable. So it has a model. So you might know this from the definition of strongly compact cardinals. And now there's Markovsky's theorem. And he showed that as schemes, we have an equivalence over ZFZ, namely Bopenka's principle is equivalent to the statement that every logic has a strong compactness cardinal. And this is again a very nice equivalence because it gives us strong reasons to accept Bopenka's principle. Because if you ask, should every abstract logic have a strong compactness cardinal? I think saying yes is a very reasonable answer to this question. Okay. So now what I want to do is I want to look at a variation of this compactness property, namely weak compactness cardinals. And you know this from the definition of weakly compact cardinals. So some cardinal kappa is a weak compactness cardinal for an abstract logic if every less than kappa satisfiable theory of cardinality kappa is satisfiable. So I restrict this compactness property to theories of size kappa. And recently, Will Boney, Stamatis, Dimopoulos, Dika Gitman, and Menachem Magidor, they studied this, the existence of weak compactness cardinals, and they showed that it's closely connected to the notion of subtleness introduced by Jensen and Kuhn, and this comes from the study of strong diamond principles in L. Okay, let me show you the definition. So it's a coherency property. So some cardinal delta is subtle if whenever I take a sequence, so the sequence is indexed by ordinals less than the cardinal, and the entries are subsets of the index. So this is sometimes called a list, right? So the gamma of entry is a subset of gamma. So this is a list. And now for every such list and every closed unbounded subset of the cardinal, we find two elements of the club with the property that if I intersect the larger entry with the smaller index, then I get the smaller entry. Right? So we have coherency in the list on this club. Okay, so if you haven't seen this before, you might want to look at this for a moment because we'll talk about this for maybe half of the talk. Okay, so this is subtleness, and so it's a large cardinal property. So these deltas are inaccessible. In fact, it's stronger than weak compactness and much weaker than measurability. So these things can exist in L. Okay. So now, once I have this, I can look at the odd version of this. So I can say the ordinals are subtle. And this is now a scheme where I say that for every class list, so I have a class function and the gamma value is a subset of gamma. And for every closed unbounded class of ordinals, I find two elements in this class club where I have coherency. Right, so this is a statement that the ordinals are subtle. So this is the scheme. Okay, and now, so this is the ZFZ result that these four people proved. So they proved it in GBC, and this is now the ZFZ version of this. So over ZFZ, together with the assumption that there's a definable well ordering of the universe, we have the following equivalence. So the ordinals are subtle if and only if every abstract logic has a stationary class of weak compactness cardinals. So this is a generalization of Markovsky's theorem for weak compactness cardinals. But this result kind of immediately raises two questions. So first of all, do we really need this definable well ordering? And so this characterizes the existence of stationary many weak compactness cardinals. So what about just asking for one weak compactness cardinal to exist? So these are the two questions. And I will show you how to answer both of these. So for the first one, so to get rid of the global well ordering, we have to look at a slight reformulation of subtleness. So it's not too hard to see that we have the following equivalence for infinite cardinals delta. So the cardinal is subtle if and only if, whenever I look at a club in delta, and I now look at a sequence, that the sequence is now not a list, so we don't have a subset of the ordinal as an entry, but now the entry is a non-empty subset of the power set of the ordinal. So I have more than one option in every coordinate, right? So this is a more general type of list, and the property that I want is then in the club, I find two elements, and in the larger collection, I find an element such that the intersection with a smaller ordinal is an element of the collection at the smaller entry, at the smaller ordinal data. Yeah, and it's not too hard to see that this is just subtleness, because in one direction, so why does this property imply subtleness? Well, if you have a list, you can get this more general sequence just by looking at singletons. And then this conclusion here is just coherency as in the definition of subtleness. But in the other direction, you use the axiom of choice, right? If you have such a sequence here, so with more than one entry, just use the axiom of, so it's non-empty, so you use choice to pick one entry at every ordinal, and then use subtleness to find coherency, and this gives you coherency in this sense. Yeah, so these are just equivalent, and it's not too hard to see it. But the interesting thing is that now, if you look at the class version, then they are no longer equivalent, because in ZFC you don't have class choice, right? So you cannot uniformly pick elements of these more general sequence. Okay, so what we do is we say that the ordinals are essentially subtle. So this is again a scheme where we say that for every class club of ordinals and every class sequence where the alpha's entry gives us a non-empty subset of the power set of alpha, we can find two elements of the club and something in the larger collection where the intersection with the smaller ordinal is in the smaller collection. Okay, and once we have this, we can show that over ZFC, it's equivalent to say that the ordinals are essentially subtle if and only if every abstract logic has a stationary class of weak compactness cardinals. Okay, so this removes the well ordering from this result. And it's not too hard to see that so if you are essentially subtle, if the ordinals are essentially subtle, the ordinals are subtle. And if you have global choice, then the converse holds. Moreover, if you are essentially subtle in V, then the ordinals are essentially subtle in L. So these two things are just equiconsistent. Right? But they can be different. So I think already in this four-author paper, there's a model where the ordinals are essentially, let's see, the ordinals are subtle but not essentially subtle. Okay, so now what about the other thing? So what if I just want not a stationary class of recompactness cardinals, but just one? For this, we have to do something more clever. And this builds up on a result that I proved together with Joan Bagaria. So now, okay.
Philip, sorry,
Yeah.
can I ask you a question?
Yeah.
So is it obvious that ORD is essentially subtle doesn't imply global well order? I don't remember if I thought about this when we talked about it, but it just popped into my head looking at this slide.
If this is, I would guess no.
That's interesting, right? I mean, I don't know. It shouldn't. I mean, I highly doubt it does, but.
Yeah, I mean, if you kind of, let's see, I guess you can cook up some example where you're essentially subtle, but you don't have a well ordering. I mean, can't you, below a subtle cardinal, you can add cone subsets everywhere, something like this, and the cardinal stays subtle. And then I guess if you cut off the universe there, then you are essentially subtle, but you have no definable well ordering. This would be my guess. I have to think about this.
Okay, I have to think about it. I didn't really follow what you said, but we can talk about it afterwards. That's
yeah, fine. Okay. But I think it should not give you a global.
I don't think so also. Yeah.
Okay.
I just want, thanks.
Yeah. Okay, so now we want to look at a different coherency property. So we look at ordinals in C1, so where V delta is a sigma 1 elementary submodel of V. So essentially it's strong limit cardinals. And what we want to characterize now is the following. So we again look at a list. So the sequence where the gamma's entry is a subset of gamma. And we look at some smaller ordinal xi. And we now want coherency in the following sense. So we want to find two cardinals where the list is coherent. So where the bigger entry intersected with the smaller cardinal is the smaller entry, right? So, and this is now kind of interesting because we no longer talk about clubs, right? So this is just at 2 points, but it's important that the points are cardinals. And it's important that I have this xi so I can get the coherency as high up as I want. Okay, so now let me ask the audience, do you have a guess what these cardinals are? Okay. I can give you one easy example is, so subtle cardinals have this property, right? Because if you have the xi, then the tail from xi to delta is a club, right? So your subtleness gives you a coherency there. Okay, so this is not the only possibility. They can also be singular. So if someone has an idea. Right? So limits of subtles have this property. And this is kind of trivial, right? Because you have this list, you have the xi, then you pick a subtle cardinal above xi, and then you just use subtleness to get coherency. Now the interesting thing here is that this is all, right? So this is somehow, I think, a very nice characterization of cardinals that are either subtle or limits of subtle. And this will motivate like the property that we'll look at next. And the first step is that this is again equivalent to the version where I allow more than one entry, right? So, and just by the same argument where we use choice, right? So we can replace like the single entry in the list by just some non-empty subset of the power set. And for this, we can now define that the ordinals are essentially closure subtle. So closure subtle means, because this property says that you're either subtle or you're a limit of subtles. So this is now this scheme where you say that for every class sequence where the entries are non-empty subsets of the power sets of the index, and for all ordinals xi, you can find two cardinals above this xi where we have this form of coherency. So we have something from the larger set and the intersection with the smaller set is in the smaller connection. Okay, and this allows us to get the desired characterization, because now we can say that the ordinals are essentially closure subtle if and only if every abstract logic has a weak compactness cardinal. So this removes the stationarity from the concept. And now one thing, but now things get kind of interesting because you have these two properties, and you can ask how are they related, right? So, I mean, of course, if the ordinals are essentially subtle, then every abstract logic has a stationary class of compactness cardinals. So in particular, every abstract logic has one compactness cardinal. So the ordinals are essentially closure subtle. So we have an implication from essentially subtle to essentially closure subtle. But what about the other way? Okay, so we now want to explore the differences between these two schemes. And the starting point for this is the following observation, that so these are both schemes, and you can kind of, it's not too hard to show that you cannot axiomatize the first statement by a single axiom, right? So if you have a sentence in the language of set theory that's consistent, then ZFZ together with this sentence will not prove that the ordinals are essentially subtle. And the reason for this, and it's the same argument as when you show that Popenka's principle is not axiomatizable by a single axiom, because you show that the assumption that the ordinals are essentially subtle, this gives you a lot of inaccessible cardinals that are sigma 1 elementary in V. So they are in Cn for a given n. Yeah. So now if you could phrase this, axiomatize this thing by sigma n axiom, then you could reflect it down to some initial segment at an accessible cardinal, and the whole scheme would hold there again, but then you could do it again, right? And you get an infinite descending sequence, right? So the first assumption that the ordinals are essentially subtle, you cannot axiomatize this by a single sentence, but you can do it with a second one, right? So because if you go back to the definition, so this statement holds if there's a proper class of subtle cardinals. I mean, this is just the argument I discussed before, right? So if you have a proper class of subtle cardinals, so this is a single sentence, and you have such a class list, such a class sequence, and you have some xi, then you just go to the next subtle cardinal above it, and you use subtleness there, and you get coherency, right? So, so this second scheme, it can be the consequence of a single sentence. Okay, but something more interesting is actually true. So we have following equivalence. So first of all, the statement that there is a sentence such that ZFC plus the sentence is consistent, and the single sentence implies that the ordinals are essentially closure subtle. So this is the same as every abstract logic has a weak compactness cardinal. Yeah, so we now assume that there is such a sentence that has this consequence. So this is now actually equivalent to the statement that that both schemes are different, right? So we know that odd is essentially subtle implies that odd is essentially closure subtle, but the fact that, or if these two things are not equivalent, then I actually get the sentence. And moreover, this is all equivalent to the statement that the existence of a proper class of subtle cardinals is consistent with the LFC. And somehow this type of result is kind of, I'm not really sure what to make of it. So first of all, I think this is the first result that I've seen where something has a consistency strength of a subtle cardinal, of a proper class of subtle cardinals, sorry. And also this type of statement that whether you can axiomatize a scheme by a single formula, that this is somehow, this has consistency strength. I think I haven't seen this before somewhere else. Okay, so this means that in order to separate these two schemes, so the scheme that every abstract logic has a stationary class of weak compactness cardinals, and the scheme every abstract logic has a single weak compactness cardinal. For this, I need the consistency strength of a proper class of subtle cardinals. And actually what we can do is we can continue to play this game and characterize kind of the next consistency strength above this. So namely, we have the following. So first of all, as a motivation, I can show that for some theory T, we have the following. So the ordinals are essentially subtle implies T. And if the ordinals are essentially closure subtle and T holds, then they are essentially subtle. So I want to aim at like axiomatizing the difference between these two theories. But this is kind of trivial because from up to here, I could just use T as saying the ordinals are essentially subtle. But now I want to say that for every axiom in the theory, the negation of this implies that the ordinals are essentially closure subtle. So somehow this should say that in a strong way, T axiomatizes that the difference between these two theories. Okay, and now this again has consistency strength. So namely, so now the question is, so I have, this is an infinite theory. And the question is, can I replace it by a single axiom? And we have the following. So the statement that there's no sentence with these properties. So it's implied by essential subtleness of the ordinals, together with essential closure subtleness that implies the ordinals are essentially subtle, and its negation implies that the ordinals are essentially closure subtle. So now this is just saying replace this theory by a single axiom. So, and the non-existence of this sentence is equivalent to saying there's a proper class of subtle cardinals and the ordinals are essentially subtle. So this is kind of the next consistency strength above having a proper class of subtle cardinals, because it's below a subtle limit of subtles, right? It's a class version of this, right? And I can again characterize the consistency of this by a statement about axiomatizing a scheme by a single sentence. But actually I cannot, so the next thing would be a stationary limit of subtle cardinals. And I'm not sure if it's still possible to find some statement of this form. Okay, but I think this is kind of very interesting and a bit weird type of result. Okay, what I want to do next is I want to tell you, so one more thing. So the way one proves this result, they also allow you to say that the existence of weak compactness cardinals doesn't imply the existence of strongly inaccessible cardinals, right? So by this result about Vopenka's principle, if all the logics have strong compactness cardinals, then I have a lot of inaccessibles and supercompacts and so on. But for weak compactness cardinals, this is not true, because what we have is it's equally consistent that there's a proper class of subtle cardinals, and I have that the ordinals are essentially closure subtle, so logics have weak compactness cardinals, but there are no inaccessible cardinals, right? And that's actually an equiconsistency. So one consequence of this is that if I want to use statements about strong logics to justify the existence of large cardinals, then I have to go large, right? Then I should talk about strong compactness cardinals instead of weak compactness cardinals, or I should say there are stationary many weak compactness cardinals instead of a single one. Okay, and the proof is not hard. I mean, what you do is you take the one direction where you prove the existence of compactness cardinals without inaccessibles. So you assume that there's a proper class of subtles, but there's no subtle limit or inaccessible limit of subtles. So every subtle cardinal, the subtle cardinals below it are bounded. So take that, the successor of this, and add that many Cohen subsets. And then in the forcing extension, there will be no strongly accessible cardinals. But I kind of starting with the subtleness in the ground model, I have enough reflection properties to find the weak compactness cardinals. Okay, so what I want to do next is I want to tell you how to prove these things, or just give you a vague idea. And for this, we need a large cardinal concept, and it has a very catchy name. So they are weakly CN shrewd cardinals. And what I want to show you is where these things come from. So the starting point is a classical result of Magidor characterizing supercompactness. So Magidor showed that some cardinal is supercompact if and only if for every larger cardinal and for every parameter in the corresponding h theta, we can find two smaller cardinals and an elementary embedding from the small initial segment to the universe to the bigger one, such that the critical point gets mapped to our supercompact cardinal and the parameters in the range. Okay, and if you don't know this, it might be easier to just look at the picture for this. And I actually used this picture 2 years ago in the talk in this seminar. Yeah, so what we do is we start on the right with kappa being supercompact and the corresponding initial segment of the universe. And then we find the smaller initial segment. And this we can embed it into the larger one such that the critical point gets mapped to kappa. So now we want to like weaken this principle and see what we get out of it. And one way to weaken this is to restrict the domain. So now the domain is now not h theta bar, but it's an elementary submodel of this. And I just assume that the universe up to the critical point is in this elementary submodel. Okay, let me show you what we get. So we look at the following properties. So we say for every larger theta, for all large theta and all parameters, we can find these two smaller cardinals. And now we find an elementary submodel of h theta bar and an embedding that now has the domain, this elementary submodel. So this X will usually not be transitive. So I have to phrase a statement about the critical point a bit careful. So kappa bar plus 1, this is a subset of X. So this basically means that everything up to kappa bar is in this model. And below kappa bar, it's the identity. And kappa bar gets mapped to kappa and the parameters in the range. Okay, so now this is a theorem. So the question is, what is this property? And it's actually two things. So first of all, and I will give the definitions on the next slide. So first of all, you can show that this is the same as being shrewd. So this is a reflection property introduced by Ratjen in proof theory. But it's also the same as being strongly unfoldable. So this is the equivalent that Gunther and Vika suggested. So strongly unfoldables came up in the work of Villavekas. He kind of studied models of set theory from a model theoretic point of view. And just let me give you the definition of these two things. So something is shrewd if and only if for every set theoretic formula and every larger ordinal and every subset of the kappa, such that the corresponding formula holds in this V gamma with the parameter. We can find smaller ordinals such that the restriction of the statement to these smaller things holds in the smaller initial segment of the universe. So this is a kind of, in some way, a maximal version of indescribability. Okay, so and Ratjen introduced this in some proof theory paper. And the other properties are strong unfoldability. So this is the miniature version of strongness, and also the miniature version of supercompactness. So what you do is you take the definition of the strong cardinal and you restrict the embedding to a small domain model. So you say, so something is strongly unfoldable if for every larger ordinal lambda and every small model, so the model has size kappa and it's closed on the less than kappa sequences, and it's a model of ZF minus or ZFC minus. Then we can find some transitive set that contains V lambda and some elementary embedding that maps the critical point above lambda. So this is really just the definition of strongness, that you restricted the embedding to a small domain model. And all of these three things are equivalent. And yeah, I think this is again kind of surprising. Okay, so now we have this embedding property, and now we want to weaken it even more. And what we want to relax is the assumption that this theta bar on the left, that it's less than kappa, right? So we can just, if we just say, okay, this theta bar can be anything, then we again get some combinatorial property, and it's again meaningful, okay, because it corresponds to something that I call weak shrewdness. And this is, you take the definition of shrewdness, so this reflecting property, but the first thing you change is that the parameters are no longer a subset of V kappa, but of kappa. And you reflect it down in a way that only the smaller cardinal, so the smaller parameter, is less than kappa, but the bigger one could again be anything, right? So this is a weakening of shrewdness, and then this modified embedding property where theta bar is now allowed to be bigger or equal than kappa. This directly corresponds to this modified reflection property. Okay, so, and this has applications. Okay. So now I want to take the last step and say what weakly CN shrewd means. So this is now this property, but I now strengthen it again by saying that if the theta I choose to start with above kappa, so this is the range of the embedding, if this has a certain degree of correctness, so if this is in CN, then I can find such an embedding. So this is the same as before in weak shrewdness, but now the domain model also has a certain degree of correctness. So the theta bar on the left is also in CN, right? And for n equals 1, this is just weak shrewdness as defined before. Okay, so this is the concept. And one thing you can show is that this does not imply strong inaccessibility. It implies weak inaccessibility, but it's not a large cardinal property in the sense that gives you inaccessibility. But using this, we can show what's actually going on in the proof of the theorems. So the statement that the ordinals are essentially closure subtle. So this is now equivalent to the statement that for every n, there's a proper class of these weakly CN shrewd cardinals. And this is then again equivalent to saying that every logic has a weak compactness cardinal. Yeah, so this is kind of the variation of Joan's result characterizing Rupenka's principle, but now for this subtle property of the ordinals. Okay, so this was one theorem, and the other one, so the odd being essentially subtle. So this is now equivalent to saying for every n, there's a proper class of weakly CN root cardinals that are contained in Cn plus 1. So they have this additional correctness property. And this, if they are in Cn plus 1, then they are actually strongly inaccessible. And this is now because of this reflection property. I just need to say that there's one such cardinal for every n, right? So I don't have to say proper class. So it's equivalent to saying for every n, there's a weakly Cn root cardinal that's in Cn plus 1. And this is then, again, equivalent to say that every logic has a stationary class of weakly compactness cardinals. And you can directly see how this being in Cn plus 1 is connected to the stationarity, because these weakly Cn root cardinals, they will be the compactness cardinals. And if your club, where you want to find a weak compactness cardinal in it, it's definable by a sigma n formula, then elements of Cn plus 1 will be in this club if the parameters are smaller, right? So this is where the stationarity comes from. Okay,
Could there be, Philip, could there be
Yeah.
like a local version of this somehow that if you look at logics of a certain complexity or something like that, that if you...
Yes.
Okay.
Yeah.
Mm-hmm.
I mean, this is one reason to prove. I mean, the other reason is I don't know how to prove it in another way. But I guess for every implication, you have to go up like 2 quantifiers or so.
Okay, right.
Or, yeah. So there's a rather tight correspondence between these things.
Mm-hmm. All right.
Okay. And now for the other results that I showed you, I also want to briefly say how to prove them. And the first example, so we have this difference, we have this combinatorial property, and the two different properties, they kind of correspond to whether these cardinals are in Cn plus 1 or not, right? Okay, but now, so some cardinal is not in Cn plus 1 if there's a larger cardinal that I can define by such a formula with small parameters, right? So this kind of basically says there is some initial segment of the universe that contains the witness for some sigma n plus 1 formula. Yeah, so something is not in Cn plus 1 if I can define a larger cardinal by a sigma n plus 1 formula with parameters in H kappa. And now we can use this to show the following. So fix some complexity and take a weakly Cn root cardinal that's not in Cn plus 1. So then we find this larger delta that we can define. And what you can show then is that, so if you take something smaller than kappa, so those is alpha, then the interval alpha delta will contain weakly Cm root cardinals for all m's, right? So basically, if you have some weakly Cn root cardinal that's not in Cn plus 1, then you also get these cardinals for all other complexities. And yeah, this is again slightly surprising, but this shows you that kind of the interesting thing also already happens at 1, right? So if you have a weakly root cardinal that's not in C2, then you have weakly Cn root cardinals for all n. Okay, so this is one thing that these proofs use. And the other thing is that this interval, something in there will be a subtle cardinal in L. And the way you prove this is that when you look at these embeddings you get from weak shrewdness, and you throw this delta into the range, then it will be in the elementary submodel that's the domain, and it will be a fixed point. Yeah, so somehow these domain models are kind of high. I mean, they are still small, but they are high. And they contain this delta, and delta will be mapped into itself. And if you are an L and you look at the least cardinal above kappa that has this fixed point property, then you can show that this has to be subtle. Okay, so this is kind of what's behind the proof that I showed you before. Okay, so now I want to, in the remainder of the talk, I want to do something, go into a slightly different direction, and this is these are patterns in the large cardinal hierarchy. So this is actually a paper that appeared on the archive this morning together with Joan Bagaria. And what we do there is, so we start from this notion like this, the ordinals being essentially subtle and these weakly shrewd cardinals. And the first thing you can do is you can give a rather precise description of how the large cardinal hierarchy looks in between strong unfoldability and subtleness. And for this, we look at the following strengthening of strong unfoldability. So this is again, so you take the definition of strong cardinal, you restrict it to small domain models, and now you make it stronger again by giving things more correctness. So an accessible cardinal is Cn strongly unfoldable if whenever I take some larger lambda that's in Cn, and I take some kappa model M, then I find some transitive set that contains V lambda, and again this elementary embedding that sends kappa above lambda. But now I have the additional thing that V lambda is a sigma n elementary submodel of Vj of kappa of n. So if n is 1, then this is just strong unfoldability, because this is a thing that elements, so if lambda is an element of C1, so then V lambda is H lambda. And so I use the fact that all of the H kappas are sigma elementary in V, right? So I use this inside of n to get this for n equals 1. But for higher n's, this is something stronger. So this is Cn strong unfoldability. And what we can show is the following. So if I have a weakly Cn shrewd cardinal, then it is Cn strongly unfoldable if and only if it's an element of Cn plus 1. Right. So this generalizes an earlier result that says if you are weakly shrewd, then you are shrewd if and only if you're in C2. And you can do it for higher complexities as well. Okay, so, and remember that these weakly Cn shrewd cardinals that are in Cn plus 1 disappeared in this characterization of the ordinals being essentially subtle, right? So now we can say, okay, we look at the large hierarchy between strong unfoldability and subtleness, and how does this look like? So this is now the existence of a subtle cardinal, and right below it, I have the assumption that the ordinals are subtle. And then below this, I start from strongly unfoldable, which is the same as C1 strongly unfoldable. And then I go up to Cn strongly unfoldables. And the ordinals being subtle is just the same as saying for every n, there's a Cn strongly unfoldable cardinal. Or I should say, odd is essentially subtle. So. Okay, so this kind of tells you a lot about the structure of how the large cardinals look like in between strong unfoldability and subtleness. But what it also does is it kind of looks familiar, right? The structure. So this looks very much like the behavior of the large hierarchy between supercompactness and Vopenka-ness, so the existence of a Vopenka cardinal. So a Vopenka cardinal is just an accessible cardinal where the second order Vopenka principle holds in the corresponding initial segment of the universe. Right, so you allow all subsets as second order objects. Okay, and what Joanne showed is that this kind of looks the same. So you have supercompactness, extendability at the bottom, and then Vopenka cardinal at the top, and Vopenka's principle right below it. And then you have this CN extendables below, and Vopenka's principle is just the same as saying there's an CN extendable for every n. But what Joanne and I do in this paper is that we show that there's even a closer connection between these two things. And you can show this by looking at a reflection property that was introduced by Joanne. So this is structural reflection, and this is the generalization of the statement of the Löwenheim-Skolem downward theorem. So this principle says, so for every class of structures of the same countable signature and every cardinal kappa, we look at the statement structural reflection for C and kappa, so SRC kappa. So this is now the statement that for every structure in the class, there's a structure of size less than kappa in the class and an elementary embedding of the small structure into the big structure. So this is structural reflection. And if the class is an elementary class, so given by a first order theory, then this holds for every uncountable cardinal. So this is just Löwenheim-Skolem. But you get strong things out of this if the classes are defined by external properties, right? Okay, so what is the connection to large cardinals? So Joanne showed that something is the least supercompact cardinal if and only if it's the least cardinal where this principle holds for every sigma 2 definable class where I allow parameters of rank less than kappa. Right? So this is an exact characterization of the least supercompact cardinal. And this goes on. So the least CN extendable cardinal is the least cardinal where this holds for every sigma n plus 2 definable class of structures. Yeah, so there's again this direct correspondence between the complexity of the classes and the large cardinal property. And moreover, so Vopenka's principle is equivalent to saying that for every class of structures, I find a kappa where this principle holds. Okay, and then what we do in this new paper is that we characterize Vopenka cardinals in this way, and this is following. This is just kind of the set version of this above theorem. So something is a Vopenka cardinal if for every set of structures that's a subset of the delta, I can find a smaller kappa such that this principle holds. So getting the reflection property out of, the reflection property for graphs out of this second property, this is almost trivial. But what is a bit harder is to get inaccessibility out of this. Yeah, so this requires some work. Yeah, but now we use the structural reflection principle to give a very canonical characterization of large cardinal properties living in between supercompactness and Vopenka cardinals. Okay, but now the same picture holds in this smaller interval between strong unfoldability and subtleness. And for this, we look at weakenings of this SR principle, and we do it in two ways. So first of all, SR minus, this is just the original principle, but I restrict it to things of size kappa. Yeah, so I only allow structures of size kappa, and they have small substructures. And the second principle was called SR minus minus by Bagaria and Verheyen. And this just says that the structure, the class C contains something of size less than kappa. Yeah, so this is a very weak statement. And the interesting thing is that, so both of them do not imply that kappa is strongly inaccessible, even if you say it holds for everything of a given complexity. But the conjunction of two things gives you strong inaccessibility. So namely, we have the following. So this is now the analog of the supercompactness result. So something is the least weakly CN shrewd cardinal in CN+1. Oh, sorry, I should say the least CN strongly unfoldable. Yeah, so that's equivalent, but that's a bit easier to read. So it's the least cardinal with this property, if and only if it's the least cardinal where these two principal holds for every class that's sigma n+1 definable with things in V kappa. Right, so this is a direct analog of this characterization of supercompact and CN extendable cardinals. But I replaced this SR principle by the conjunction of these two things. Okay, and then there's the version of Popenka's principle here. So the ordinals are essentially subtle, if and only if for every class of structure of the same countable signature and every natural number n, I find some element of Cn such that this SR minus holds there. I mean, there's a small variation here, but it's, I mean, so let me get back. You want to write SR minus minus there. And actually SR minus minus for all sigma one definable classes with parameters in V kappa, this gives you that you are in C1, so you're a strong limit. But you need to go through all the parameters, so you look at different classes. So you can, in this statement, you kind of collect it into the statement that you're already in Cn. Okay, so this is the version of the characterization of Popenka's principle, but now for essential subtleness. And we can also do subtle. So something is an uncountable cardinal is subtle, and now we have the thing, the variation of the thing we had for Popenka cardinal. So for every set of structures, that's a subset of V delta, I can find a smaller cardinal kappa, such that these two principal hold at kappa. Yeah, so, and this gives you subtleness. And again, it's actually quite a lot of work to get inaccessibility out of this reflection property. Okay. So, but this shows that just by restricting this structural reflection principles, you can show that this interval at the top has the same structure as the interval at the bottom of the large cardinal hierarchy. And you can do even more, but I will only say a few words about this. So what you can do is you can look at work of Bagaria and Trevor Wilson. And Trevor introduced this notion of product structural reflection, which is a bit weird, but it's also a weakening of SR. And what Joanne and I showed is that for this notion of product reflection, the same pattern holds between strongness and woodiness, right? And again, if you can find the kappa version of product reflection, and if you go down again, you again go to the interval between strong unfoldability and woodiness. So what we have is, so we have the large cardinal hierarchy, and we can roughly divide it into three parts. So saying, okay, the bottom is some things that can exist in L, so up to zero sharp. And then we have the things that can exist in canonical inner models, so up to something like subcompactness at the moment. And then we have the really strong stuff above this. And if you look at this interval from supercompact cardinals to Popenka cardinals, then it has the same structure as the interval from shrewdness or strong unfoldability to subtleness. And this again has very much the same structure as the interval from strongness to woodiness. And I think this is quite interesting because if you look at the context in which, for example, subtleness was introduced, so this were like combinatorics in L, So this is very different from like where wooden cardinals come from, or Penka cardinals come from. But you can show that these things are all just instances of one pattern. And yeah, I think that's quite interesting to see that how these things connect. Okay, and let me just show you one more slide. I mean, one byproduct or several byproducts of this analysis is that they tell you a lot about new facts about subtle cardinals. And kind of the slogan for this is that these things are actually can be seen as miniature versions of Popenka or wooden cardinals. And for example, what we get is our embedding characterization for these cardinals. We show that something is subtle, and there are many ways to phrase this, but I want to make it as much as look like the characterization of wooden cardinals as possible. So we say, so we have a function from delta to h delta. So for every such function, we find some smaller cardinal kappa that's closed under this function. And for every larger gamma and every transitive domain model kappa of size m of size kappa that contains the initial segment of this function, we can find a transitive set n that's higher than gamma, and an embedding from m to n that maps this function f correctly. So so this initial segment, if we restricted the image to gamma, it will just be the initial segment of gamma up to f. So this is kind of the embedding property you get for strong unfoldability, but you get this wooden-like property that you have correctness for these external f's. And there are many ways how you can modify this, but this is maybe the one that looks the most like embeddings for wooden cardinals. Okay, and this is kind of what this analysis also gives you. Instead of saying there's a nice picture, you get like new technical facts about subtle cardinals. And I think you can use this, for example, to prove indestructibility results for subtleness, because I think everything you can prove for wooden cardinals, you can prove it for subtle cardinals with these embeddings. Okay, and this is all I wanted to say. Thank you.
Thanks very much, Philip. Really great talk. So many interesting things. All right, questions? Anyone? All right, going once, going twice. All right, then thanks again, Philip.
Thanks for having me.
Let me stop the recording.